Let's see, let's get prepared here. All right, last chance. I hope these are here. Let's see. Okay, here we go. Parametric. I guess this doesn't matter. I'll just start them. Okay, so we're talking about parametric functions. What are parametric functions? What's the gist of that? What's that?
There's an invisible axis t.
Okay.
And y and the functions y and x are related to t.
Yeah, so instead of y being dependent on x, which is what we're used to, now x is dependent on some new variable t and y is dependent on some new variable t. And so as t changes, that generates ordered pairs, right? So every t value generates a new point. And then we still graph in the xy plane, still graph points in the xy plane. So here's an example. 8t minus 3 and negative 6t minus 2. Okay, so x equals 8t minus 3, y equals negative 6t minus 2. So we'll start by, let's write that. Can you write that as an equation of y and x? So y in terms of x. We'll start by doing that. Remember how to do this? So what's the idea? Eliminating t. You're eliminating t to just relate y and x without t. And then you want y in terms of t. Sorry, y in terms of x. Y in terms of x. Okay, and so how do we do this? Remember what we said? Yeah, Alec.
Have x equal to 18 minus 3.
Right.
Add the 3 to the x.
Okay.
Divide by 8, you have t equals x plus 3 over 8.
So you got t equals x plus 3 all over 8, okay?
Plug the t into the y function, you get negative 6 times x plus 3 over 8 minus 2.
Negative 6 times. Right, because if y is negative 6t minus 2, then it also must be negative 6 times x plus 3 over 8 minus 2. Okay, and if we want, we could make it look like what we're our mx plus b. If we do, maybe what, negative 3/4 x. And we got, what is this? 18/8 and minus 36, minus 54/8, minus 27/2. 17/4. If we do the math, we can make it look like that. Okay, so suppose we started with this though. Okay, so this is the y equals, a function of x form of this parametric function here. So looking at that form, what do we expect the graph of this parametric function to be? Yeah, so we clearly see this is y equals mx plus b, and this is equivalent as a set of points to this, so this is going to be a line. Okay, so what if we were given this line and we needed to come up with the parametric form of it? So we wanted to write this function y in terms of x, but we wanted to write it as a parametric function. Well, if you look back, there's really nothing here. Negative 3/4 x minus 17/4. There's really nothing that indicates this. 18 minus 3 minus 16 minus 2. That's not clear at all how those two are the same. Would you agree? So we kind of take a different approach then. So whenever you have y in terms of x like this, one way you can write it parametrically is to simply let x equal t. So this is a technique you can use. If you have y in terms of x, you can let x equals t, and then what would y equal? Negative 3/4 t minus 17/4. And there you have a set of parametric equations that also is equivalent to that line y equals negative 3/4 x minus 17/4. Okay, so question. Is this parametric function the same as this parametric function?
It would return the same values, right?
It would return, so when you say values, what do you mean?
Values is in x, y coordinates.
He said it would return the same
But for different values.
ordered pairs. It would return the same set of ordered pairs. Is that true?
Have the same range.
So what does this, so this is a line, right? And what does that line consist of? Points, right? It's a set of points, and each of those points has an x and y coordinate. Okay? So what about this function? Is it the same set of points as this one? Okay. What about this function here? Does it give the same set of points as this one? Yeah, it does. So they do give the same set of points, right? Both these parametric functions are going to give the same set of points that is defined by this line. That's my original question. Are they the same function?
Well, because it would give you the same points with different values of t, though.
Okay, so let's investigate this further. So first, let's take a look at this line. So we all could sketch this line here, but let's just see that.
It's like if you did it domain shift.
Okay, so here is this line, negative 3/4 x minus 17/4. Okay, but I'm graphing it as that first what we started with, parametric function that we started with. Okay, and so now if I graph that line, it should just in red I will graph the line y equals negative 3/4 x minus 17/4. And so what should happen? Same line. Purple, indigo, right? Red plus blue. So it is indeed the same line. So we did the math right. So to investigate this question, are they the same function? Let's start talking about a little calculus here. So what would dx dt represent? So this is our blue line. So from this set of parametric equations, let's think about dx dt and dy dt. So what does it mean? So what would, if we were to find dx dt, not what does it equal, but what would it mean? What would it mean? Okay, that's what it's called. What would it mean?
How rate of change x changes to t.
Okay, what's
How x changes a little bit from changing t.
how x changes with a little change in t. What'd you say, Adrian? Right, so the rate of change of x with respect to t. So yeah, so meaning if we increase t a little bit, this is going to tell us what x will do. So what is dx dt for this initial set of 8? Okay, and what is dy dt? So what does this tell us? For a change in t, what's going to happen? For a little change in t, what's that?
X will change 8 times.
Good. X will change 8 times as much. And can you? How will it change 8 times as much? Like,
Proportion. What's the
but
question?
like so. Notice this has a negative and this is positive.
Oh, positive. It'll increase.
What does that mean? Increase to the right, right?
To the right.
So for a change in t, x will change 8 times as much. What to the right? And for a change in t, also, y will go change 6 times as much down. Okay. Now let's do the same thing for this over here. So what's dx dt for this one? 1. Dy dt is?
They represent the same set of points.
Same set of points, but
They have different derivatives in respect to x. But could you do a derivative that's in respect to both x and y that would be the same? Or is that?
so dy dx is y with respect to x.
Okay.
T wouldn't be involved, so there would only yeah.
Aren't they still actually changing at the same rate to each other though? Because if we multiply both by 8, we just get 8 and -6.
Yeah, because dx, dy, dx.
Relative to one another,
Yeah.
right? So let me show you. Oh, I didn't want to do that. We're back. I want to do this. I left my adapter at home, so I'm hooked up to the computer adapter, which is short. All right, so do this. Make that one blue, because that's our blue one. And then what was and what was it? -3/4 n -17/4. I did that in black. I'll just do it. Okay, so red. So this one's red. This is our red version. Okay, and then this is our blue version up here. Okay. Watch. So now we're gonna let this thing graph one point at a time. Let's let that go from. Let's be good on that, but we'll see. Ready? No. A lot more steps here. Okay, now we got it. So watch what's going to happen. So this is our value of t. So as now I've got t changing, here's the red version, right? dx dt equals 1, dy dt equals -3/4. There goes the blue version. Let's make it for a smaller range here. Negative. Try it again. So this is the second version, generating points. The value of t is there, -1. Okay, and then that's the points being generated by the blue curve. Why? Because for a change in t, x is going to change by 8, and y is going to change by 6. As opposed to the second version, for a change in t, x is going to change by 1, and dy dt or y is going to change by -3/4. So they both generate the same set of points, but in a very different way. You see that? Different values of t are generating the points differently, and it's kind of like the blue one is generating those points a lot faster, right? So for changes in t, you get a lot bigger change in. So where does that happen here? From like 0 to 1. Okay. Do -1 to 2. Okay, here we go. So for -1 to 2, see, these are the points that the red function is generating. The blue function generates all these points that you can see and more. Okay, but the red function only generates a little piece of the line here, whereas the blue function generates a whole lot more for those same values of t. Why? Because x and y are changing a lot more rapidly with respect to t than for the red function. So same set of points, but vastly different functions, right? In the way that those points are generated. Okay, and so these meanings of the derivative are important, understanding what dx dt and what dy dt represent. Any questions on that? And so that's what we see with parametric equations. Given a set of points that you want to generate, there could be many different parametric functions that generate the same points, but just in a different way for different values of t. Yeah.
How would you find out where those, like the exact point that those two functions intersect at the same t value?
We could just see where they overlap here. Somewhere around. So I'm cheating. You're asking for a mathematical way to do it, right? Yeah. So that's what's called a collision point, right? So a collision point is when the same value of t generates the same. That's a good point. So let's mention that. So a collision point. The value of t gives the same ordered pair in two functions. Okay, an intersection is then just simply that the ordered pair is generated by both functions, but by different t's. It doesn't have to be. So intersection is any time that two functions generate the same ordered pair, whether it's a collision or not. So same ordered pair, regardless of t.
So is that just like 37?
So every single point on this line is an intersection point, if we're talking about these two functions. Why? Because they generate the same set of points. But there's this one collision point. There's this one point somewhere around 0.4. Somewhere around 0.4.
I think it's 3/7.
What's that?
3/7.
How'd you get that?
Set the x's in terms of t into each other. So
And then they should make the y's as well. Yeah, so yes, it's we're for what value of t do you get the same x? You take at minus 3 equals t. And then that value of t should also generate the same y value in both. So you said it's what? 7 over 4? 3/7, which is around 0.4. That's right. So if I do n equals 3/7, they land right on top of each other. Okay. So normally you would talk about intersection points for different sets of points, right? So this is a little bit strange situation because every point on this line is an intersection. So normally you'd have two like curves, and they would have some points of intersection, and that's what you're interested in. And then if it's a collision point, if the same value of t in each function gives you that same ordered pair. Okay, let's do a new example. Any other questions on this? So what we're seeing here is that writing a function parametrically, it kind of opens up a lot of new things to think about when it comes to graphs and derivatives. Okay, this is a new arena, right? So there's new things to investigate. Okay, so let's look at this one. Two sine 6 pi t and cosine 6 pi t. Okay. So here's a parametric function, and I want to write this as I want to express this as y in terms of x. Y in terms of x. Okay, so what did we do before? We took the x1 and we solved for t, right? And we plugged it into the y1. But what will happen here if we solve the x1 for t? What will we need to do that? Inverse sine. And so inverse sine, it's a weird thing because of domain and range issues, right? We have to cut the domain of sine in order for the inverse sine to be a function. And then we're going to have cosine of inverse sine, and this isn't a very natural or friendly way to deal with this, right? The cosine of this inverse sine of something. That's very constrictive, and it doesn't really lend us much. So we need another way here to eliminate t. Any ideas how else would be another way we might be able to eliminate t rather than solving one of these for t? Any ideas? So what if I did this? What if I wrote, so wouldn't it be true that x over 2 equals sine of 6 pi t? And then y equals cosine 6. What am I trying to do? I'm trying to eliminate t. So is there any way I can combine sine and cosine and eliminate t?
Could you take the derivative of x over 2 and get it to cosine so that they're similar? And then
But then we'd be relating the derivative to y. What was that?
Use one of the trig identities.
Okay, maybe a trig identity could help. So, what's the first and most important trig identity? Sine squared plus cosine squared equals. So 1 certainly eliminates t, doesn't it?
Just do 1 minus cosine. Is that equal to sine?
So we want to get 1. We don't want to do 1 minus. We want to get 1. Because you do 1 minus one of these, then you still got t's involved. So what is sine squared in our case? What is sine squared of, so now I'm going to make, my theta is going to be 6 pi t, okay?
X over 2 squared.
Yeah, so sine of 6 pi t is, sine squared is going to be x over 2 squared, right? And what's cosine squared? Well, if that's sine squared and that's cosine squared, then what do they equal? Equal 1, right? See what happened? So I just took sine squared of 6 pi t, let theta be 6 pi t. As long as these angles match, that can be any angle, any argument there, as long as they match. Then this squared plus this squared equals 1. Well, that's going to be x over 2 squared plus y squared. That's going to equal 1. Right? So what am I going to have? What is this? You guys recognize what that is? It's circle-ish. What is it? That's an ellipse, right? That's an ellipse. And our general form of an ellipse is x squared over a squared plus y squared over b squared equals 1. And a and b are called our directrix. So a is like the radius in the x direction, and b is the radius in the y direction. So what do we got? So we got a equals 2. So I'm just going to sketch this first by hand, and then we'll plot it. And then this is like y over 1 squared. It's going to be 1. So this ellipse is going to be longer horizontally, twice as like this. So let's graph it. Let's see that. Okay, so there it is. So new example. So I want you to write this ellipse in parametric form. So I want you to write, where is it? 16x squared plus y squared over 9. So take this thing we just investigated. So write that in as a parametric function. Okay, before you do that, sorry. Put that on hold for a second. Let's talk a little bit more about this blue one, the one I did at first. So what's the difference? What's the difference between this parametric ellipse versus writing it in as the equation of ellipse of x and y? So what is there a distinction between them? Okay, so we're going to say 2?
They like oscillate. Like the x is just going to go left and right. But if you have lines, you see that it's up a little. I guess if it were up,
Okay, so you're thinking this has like movement or something like that? Yeah, so right, for changing t, these points are generated in a certain way, whereas this just represents, boom, all the points, right? These aren't really, there's really no direction or, yeah. So what is the direction then? So then what is the direction of this? So one way we can find that out is, so looking in blue still. We could just find a couple t's and just see what happens. So for instance, because we got the 6 pi in there, I'm going to do t equals 0. And then because of that 6, I want to make something really small, so like 1/12. So at t equals 0, what point do you get? What point do you get at t equals 0? 0 and 1. So when t equals 0, you get the top of that ellipse. You see that? So this is t equals 0 right here. And then when t equals 1/12, what point do you get? So it's going to be 2 sine of pi over 2, right? Pi over 2, and then cosine of pi over 2. So that will be, what's sine of pi over 2? 1 times 2 is 2. Cosine of pi over 2 is 0. So what's the direction of the curve? Clockwise. Okay? How else might we determine, instead of finding individual points and then just kind of seeing how they trace out, what would be another way possibly to see what the direction of the curve is? What's that?
Take a derivative.
Would a derivative help? So what about dx dt? What is dx dt? What? Actually 12 pi cosine of 6 pi over t, or 6 pi t. And then let's look at 0. So let's evaluate that at 0. What is it? 12 pi times 1, or 12 pi. So I got when t is 0, dx dt is 12 pi. Does that help me find the direction?
Well, you know it's positive, not negative.
Okay, is it positive? So this is showing me that dx dt is positive. When t equals 0, does that show the direction? For a change in t, x changes, it increases, right? It increases. If it's positive, for a change in t, it's heading to the right. That tells us the direction, right? That tells us that it's clockwise. See that? So if you have a positive dx with respect to t, that means for an increase in t, x is going to increase, and increasing x is to the right. So that means that that also confirms it's turning clockwise. If we were to take dy dt and plug in 0, what would we expect?
0.
Why 0?
There's no change in y at that point.
Good, right. So if you do dy dt and you plug in 0, you're going to get 0, which means what? In the y direction, it's pausing, right? So in the y direction, it's pausing. And so that would be inconclusive, right? You get dy, you wouldn't know if it was going right or left, because in both directions, your y value would pause at the top, whether it was heading right or left. So the dy dt in that case would be inconclusive. But the dx dt tells us clearly, since it's positive, it's clockwise. Okay, now let's do your other example. So we're going to start this red example here. Given this ellipse, right, another ellipse, can you write it as a parametric function x equals and y equals? It's not. That's y squared divided by 9. So here's your hint. If you don't know how to start, make it look like this. If you can make it look like that, you're home free. And you can just write down the answer. If you can make it look like that. Well, not entirely. You still have another step after that. But your hint is make it look like something all squared plus something all squared equals 1. And then introduce sine and cosine. Don't have to whisper. Whenever I put you to work, you can always collaborate, you guys. Always. Always.
Shouldn't matter inside. Like as long as t is inside the parentheses or sine, and they're the same, it shouldn't matter. Like 6 by t, just t. Because either way, you can do that as you want. It's just how t behaves. How it makes sense. How it makes sense. Like it's the column.
Okay, so what was it?
What was what?
16x squared plus y squared over 9. Okay, so we want to write this as something squared plus something squared equals 1. So what is it for x? Should see that easily. And y over 3. Okay. So what are we going to do? What also is such that something squared plus something squared equals 1?
So 4x equals sine t.
Yeah, so take 4x, and you can make that equal to sine t and y over 3 equal to cosine t. Are we done? Almost. We need x equals and y equals. X equals sine t over 4, or 1/4 sine t, and 3 cosine t. Okay, what's the starting point? T equals 0 is which point? Was it? 0, 3. Okay, and let's just confirm here. So what is our, this is like x squared over what, 1/16? So a is 1/4, right? This is x squared over 1/16 and y squared over 9. So our a value is 1/4. So that's like our, on the x-axis, is like our radius on the x-axis. And our y squared over 9, so our radius is 3. So when I graph, so we're going to graph it here. So what did we say? 1/4 sine t and 3 cosine t. I'll do it in blue. Nice and line right on top of each other. And need to show more. So I'm only showing t from 0 to 1 here. So this is that blue little part. That's only when t ranges from 0 to 1. So I need to range from t from 0 to what? 2 pi, right? So now they're the same.
I'm sure 360 would come up.
Yeah. Okay, so was this the only way to do it? So here I am at this step right here. 4x squared plus y over 3 squared equals 1. Is there any way else I could do that? What's that, John? No. Yeah. So that brings square roots in, plus or minus. We still want to use trig, but as
Switch cosine and sine,
yep.
or you could change anything inside the parentheses for both of them as long as x and y are the same inside the t parentheses and t is inside the parentheses. That probably made no sense.
Yeah, we lost you. Or you lost us. Okay, so that'd be another way, and then we'd have x is 1/4 cosine t, and y is 3 sine t. Same function or different function? Same or different? Yes, right? Same or different? Yes. How are they the same? They're going to plot the exact same set of points. But how are they different? How they do it, right? So now if t equals 0, what do we got? We start at 1/4 0. So now when t equals 0 for the second, we're going to be here. And we could confirm that they're going in different directions as well. The first one is like the first example we did. It's going to go clockwise starting from the top. This one is going to go actually counterclockwise because x is cosine. This is, these are our definitions of cosine and sine. Cosine being x-coordinate, sine being y-coordinate. We know that that starts at the x-axis, angle increasing in the counterclockwise direction. So this is going to be counterclockwise. That first one is going to be clockwise. Is there another way we could do it? Notice these are squared, right? These are squared. So what could be another way we could do this? Noting that these are squared. 4x equals. What else squared gives sine squared besides sine t? No, what else squared? What else, if you squared it, would give sine squared other than sine? What's that? No, 4x. 4x is still 4x, but but you got the idea. Negative sine. I could do 4x is negative sine. I could do y over 3 is cosine. Or I could do y over 3 is negative cosine. Or I could do 4x is negative cosine and y over 3 is positive sine. There's actually, how many different ways? 8. There's 8 different ways to do this by switching sine and cosine and switching their SIGNs, right? Plus or minus. There's 8 different ways to set this up. No, 4. This could be
Just change the range.
4. Sine or negative sine. Oh no, it is 8. It is 8. Because this could be sine or negative sine. This could be cosine or negative cosine. And then for each one of those, you take the other function plus or minus. So we could have cosine and then plus or minus sine. Then we could have negative cosine and we could have plus or minus sine again. So there's 8 different ways that we could fit in plus or minus sine and plus or minus cosine into these to get a function. They'll all start at different points and have different directions. Okay?
If you don't limit yourself to just t as an argument for sine and cosine, then after like infinitely,
Yeah, but then you're just changing the symbol. It doesn't really change the function. You're just changing what you're calling the independent variable. So
No, I'm not like t as in, like, couldn't you do 6 pi t and 6 pi t for both? Would that change?
oh yeah, right.
Or
Yes.
like anything as long as
Right.
they equal each other.
So Mark, to find the direction, let's say we take the derivative of 3 cosine t, where you get 3 negative sine t value.
Which one? Which one? Here, up here.
Yeah,
If you want to do dy dt,
yeah, so we get 3 negative sine
uh-huh,
t evaluated at 0.
and that'll give 0. Or that'll give 0.
No, I'm sorry, so then we take 1 round sine t.
So this one would be dx dt.
Yeah.
We get 1/4 cosine t, which would be 1/4.
Assuming it's mentioned.
That's positive. dx dt is positive. So for a change in t, x is increasing to the right. But that's also because we're at the top. If you had that same thing at the bottom, then and it was positive, it would be counterclockwise. Because an increase in x down here would make it go around this way.